Good day, everyone. Mr. Armke back with you for CTI 120. Today we're going to be talking about Chapter 7, Virtualization and Cloud Computing. Our objectives today are to talk about and explain virtualization technologies, including how VMs connect with the network and how networking infrastructure devices can be virtualized. We're also going to discuss cloud computing categories and models and discuss some concerns regarding connectivity and security. And then we'll mitigate that with some network connection security methods using encryption protocols and how to set up remote access connections between devices. So what is virtualization? The virtual or logical version of something rather than the actual or physical version. So constructing it in software rather than in hardware. The term that we use for the physical computer that is containing or providing space and resources for the virtual machine is called a host. Each virtual machine within that is called a guest. The hypervisor is the supervising software that manages and creates a virtual machine and manages resource allocation and sharing between a host and any of its guest VMs. There are two different types of hypervisors that we will run into. What's called a Type 1, also called a bare metal. Bare metal hypervisors install before the operating system, so the hypervisor in and of itself acts as an intermediary to contain the operating systems of the VMs. And a Type 2, which is probably the most common that you'll deal with in the beginning, installing a host operating system and then an application within it. So the Type 2 is often called a hosted hypervisor. Now, a VM's hardware and software characteristics are assigned to it when it gets created in the hypervisor. You can then customize the VM with things like a guest operating system, a specific amount of memory, a virtual hard disk of a particular size, processor types, and other various options. Now, if there are specific functions of that processor that you want the VM to have, that will need to be something that is not necessarily directly supported natively, but compatible with your host CPU. Every VM also has what's called a vNIC, virtual NIC. Now this can connect the VM to other machines and operates at OSI layer 2. Each VM can have several vNICs, the maximum number depends on the hypervisor of course, and when the VM's vNIC is selected, the hypervisor creates a connection between that VM and the host. The connection could be called a bridge or switch, vSwitch. See here in the graphic for 7.5 the connection between a physical NIC, a virtual switch, and a virtual host within the VM. One host, of course, can support multiple switches. Again, limitations here are solely at the behest of the hypervisor. So finding a good hypervisor means that there'll usually be a lot of options to be able to customize your machines. The way a vNIC is configured determines whether the VM is joined to a virtual network or will attempt to use a pass-through in order to join the physical LAN that the host machine is connected to. There are a number of configurations called networking modes. The most common are bridged. Then we have NAT, network address translation, and what we call host only. Bridged mode is where the vNIC will access the physical network using the host machine's NIC. It obtains its own IP address, its own default gateway, and its subnet mask from the DHCP server on the physical LAN. So it's not relying on the virtual switch internally at all. The VM appears to nodes as just another client, so there's no indication that it is actually a VM. In NAT mode, the vNIC relies on a host machine to act as a NAT device. So it's going to obtain its IP addressing information from the host with the hypervisor acting as a DHCP server. This is more appropriate for VMs that don't need to be accessed at a known address by other network nodes. Here we can see in figure 7.9 the vNIC accessing the virtual interface for the physical network. So we can see VM1, for instance, goes to vNIC1, connects to the virtual switch, where the DHCP service is connected, and then the physical NIC translates that to the physical network. Here in the right-hand side, figure 7.10, we can see VirtualBox settings under the network tab to enable or disable the network adapter, and in this case it is attached to NAT. A little callback, we can see that there are 4 different adapter tabs set up. So that is the implicit limitation for network adapters for VirtualBox for this particular machine. Host-only mode is where VMs on one host can exchange data with one another and with the host itself. They cannot communicate beyond the host, and they'll never receive or transmit data with the host's physical NIC. So this would be more so if you just wanted to create a virtual network inside of the VM itself, or the VM host rather. So in this case, VM1 can communicate with VM2 as well as the host, but nothing in the physical NIC. So let's look at some advantages and disadvantages, pro and con it a little bit. Virtualization is a much more efficient use of resources by separating multiple machines from one single physical machine. There is some cost and energy savings, especially if you have a very low weight OS and very small interfaces for things. Tends to be a lot better than running individual physical machines. There's also a lot more fault and threat isolation, so we can kind of keep things away from potential external sources of damage. And there's also some layers of separation to where if something does get breached, if we have our security software set up correctly, we can cut it off before it gets to anything of value. It's also a lot easier to do backups, recovery, and replication because the operating system and all of the contents tend to be contained into what's called a virtual disk image. Sometimes it'll be a VDI, there's a couple of different versions, but in general, you have these virtual disks and a configuration file. Then you can copy and duplicate that as you please and set up multiple instances of the same VM. This type of operating system dumping into a hard disk file that is just essentially a storage medium on the disk, an ISO, if you will, a disk image, is a big part of how forensics operators and technicians will try and crack cell phones and laptops and things like that. They'll create a disk image that can be infinitely reset and manipulated. The disadvantages of virtualization is that there are some compromises to performance. Anytime you're doing something inside of another software system where there's a bit of translation, you're not going to get optimum performance. Now, this is usually not super noticeable unless you're running a huge number of VMs on the same machine. There is an increased level of complexity, so there's a lot more going on to where the hardware has to kind of divvy up its resources accordingly. Let's say that you have a system with 4 RAM sticks, a quad-core processor, and a pretty decent-sized hard drive. We are essentially pulling all of those resources in 4 different directions. The RAM is being divvied up, the processor is being divvied up, etc. There's also licensing costs. If we have multiple operating systems and we need to license them, now we have to license however many are there instead of just the one. There is also a single point of failure. Even though we have multiple VMs inside of the host itself is a single point of failure. Now, there are some options we have for virtualizing network devices. This is part of what's called NFV, or Network Functions Virtualization. We can use a virtual firewall, which is where a firewall's OS and a VM can be installed to an inexpensive server. A virtual router, this is where you install a router VM on a server instead of purchasing an expensive hardware-based router. The advantage here is that virtual devices can be quickly and sometimes automatically migrated from one server to another if something fails, or if we have a maintenance situation where we have to switch out a hard drive, or if we're trying to expand, things like that. Resources are also utilized much more efficiently. The hard disk for a virtual machine can be set up dynamically to where it expands or contracts and thereby provides elasticity, allowing it to use only the space that it needs rather than spinning up an entire disk. Services are also more easily scaled to meet the changing needs of a network. So NFV allows us to merge physical and virtual network architectures, lots of flexible cost-saving options for different types of network devices such as virtual servers, load balancers, data storage, and firewall protections. Now keep in mind, for each device, as I said a little bit earlier, you're going to need licenses. Now if you're using open source software, this isn't so bad, but if you're working for something that's a little bit more expensive, we do have to keep that in mind. Interaction between physical and virtual devices also introduces a small degree of latency, so that's some of that performance loss we were talking about. Some administrators are also not comfortable using a virtual firewall to protect an entire network. I know I personally prefer to have a physical firewall. It tends to be a little bit more robust, a little bit less susceptible to certain types of overflow attacks, things like that. Now, this is not to say that you could not, by introducing an even further degree of latency, have a virtual firewall as well as a physical one. You can stack these types of things. Software-defined networking, or SDN, is the virtualization of network services. So we talk about what's called an SDN controller managing these things, also called a network controller in certain cases. These are going to manage your services instead of the services being managed directly by your hardware. So an SDN controller is going to integrate all of our virtual and physical devices into one cohesive system. We have protocols that handle the process of making decisions. This is called the control plane. You can see it rendered in that kind of yellowish tan color in the graphic below. Physical devices will then make contact with data transmissions as they move across the data plane, rendered in blue, and then the actual devices we see rendered in gray. So we have just kind of these what are called abstraction layers passing data in between them. So on the left we see a traditional system where the data planes are interconnected, and then we have a pass up or down into the control plane or the physical interface of the device. On the right hand side with SDN, we see that the control plane is unified. Each of the data planes are linked together in a mesh style scenario, and then each of the devices are separated into their standard settings. So the only thing that really changes is unifying the control plane versus having it separated. So here we see the way that the SDN controller operates in decision making from the application layer, so that's up at layer 7, as you recall, the API, which is the structured programming interface, allows us to pass things down to the control plane of the SDN controller. So this is where all of our routing, switching, blocking, and forwarding will take place, and then the data and control interface will pass things down to layer 1. So that's where we would have our virtual switch, router, or physical devices. Now, our primary advantage to separating the control and data planes is to provide the network technician with more centralized control for our network settings and various types of management. SDN creates the potential to implement more sophisticated functions while using less expensive devices, so trying to improve functionality while reducing cost. SDN architecture has been expanding to include management of network resources hosted in other places other than the organization's own network. So that leads us pretty neatly to cloud computing. Cloud computing is a very common term we hear nowadays, but not a lot of people understand what it actually means. The internet is often pictured as a cloud, as a graphic. So if we look at network diagrams throughout the previous chapters we've seen, that is definitely something we've looked at quite a bit. The cloud computing process is referring to the flexible provision of data storage, applications, and services to multiple clients over a network. Cloud computing has various features that we may wish to implement for our network, such as on-demand services, support for multiple platforms, resource pooling and consolidation. You'll see that a lot for data storage, as well as distributed processing for very large data clusters. Metered service, so you only pay for what you need rather than having to invest in a big physical infrastructure. And elastic services and storage to where we can scale capacity up or down very quickly, if not automatically in certain cases. Cloud computing can also provide us with virtual desktops where the operating environments are hosted virtually, and you link into them the same way that you would with any other web browser style interface. Developers can load any kind of software on the servers and test it from afar, and thus the cloud services provider can make sure that the development servers are secure and regularly backed up. Now note the beginning of that phrase. The cloud services provider is responsible for this security as well as for data backups. That is something that is considered to be a limitation of cloud computing, that you are placing the burden of your security and data redundancy on someone else. Most cloud service providers use virtualization software to provide multiple platforms to multiple users. So if you want something to run Linux, something to run Mac, something to run Windows, something to run something like Peregrine or a smaller OS, that can be done in a virtual environment using all of the same hardware. So here we see cloud computing implemented. We've got some different devices, laptop, tablet, smartphone, could be anything. We have on-demand access from any location, and multiple platforms supported. Everything passes through the virtual server, which is just kind of a request processing interface. That server passes over to whatever services are offered by that particular company. So application, storage, collaboration, access control, elastic provisioning of resources, security, backups, and then of course it can handle multiple users simultaneously and independently. The nature of virtual machines, especially when implemented correctly at the hardware level, makes sure that there's no overlap between tenants. Now, cloud computing service models are traditionally categorized by the types of services that are provided. A traditional cloud computing service model is where everything is located and managed at the organization's location. So that's where everything's hosted at home, if you will. Infrastructure as a service, or IaaS, is where hardware services and network infrastructure is provided virtually. So it will include user interfaces such as HVDs, hosted virtual desktops. So we can see down there at the bottom of the second column where the vendor management kicks in. We can see the applications and data storage are local, and the OS down is going to be by the vendor. PaaS deals with a platform as a service system where we have the OS, runtime libraries or modules for the OS, and the hardware virtualized as well. Now we see that the little bit of difference between the IaaS and PaaS is that the IaaS partially includes the OS, whereas the PaaS is going to have that inclusive as part of its management services. So think of it almost like in the IaaS as you would between layer 2, the Mac sublayer and the LLC sublayer. And then as far as software as a service, that's just going to be the application itself. So that's a direct interface for something that's completely hosted on the cloud server side. There's also what's called XaaS, everything as a service or anything as a service, depending on your definition. It's a much broader model. The cloud can provide any combination of IP or SaaS systems. So we see SaaS can be used to manage email, social media, online games, and customer retention or resource management. PaaS can give us our web-hosted databases and servers, and IaaS can give us some storage as well as VMs. Now we can see here that the categories kind of get inverted here in terms of the topography. We can see that SaaS is immediately accessible to end users, whereas PaaS is mostly for application developers. And then IaaS, of course, is more so for network architects. Cloud services are delivered in a variety of different deployment models, what we call public, private, community, or hybrid clouds. Public cloud is where the service is provided over public transmission lines. A private cloud is established on an organization's own servers in its data center, so it is retained locally. The community cloud is shared between multiple organizations, and then a hybrid is a combination of any of the other service models into a single deployment. So you could have some that have an aspect of a public cloud as well as community cloud, or even all three. Now let's look at some risks and limitations, of course. The uptime and bandwidth limitations of your ISP, the uptime and backup and security systems of your cloud provider, a little callback to what we talked about previously, misconfiguration that could expose data between clients, unauthorized access to data by cloud provider employees or illegitimate users, confidentiality breaches, data security regulations. This is especially true if you have a cloud platform that operates internationally. Do you support, the UK's data protection services versus the ones that are here in the US? The state of California has slightly different data regulations than the rest of the country. We have issues over ownership of cloud-stored intellectual property, questions over data maintenance, risks to the network, proprietary data, or customer information via what's called a BYOC, or bring your own cloud service. So bringing your own cloud in basically means that you're using cloud storage for another company to connect to a cloud platform. So that can be potentially messy as well. So every device that a customer uses that has multiple cloud services could bring some potential risks. There's also reduced customer confidence, fines, and legal concerns when a cloud breach occurs, because it's very difficult to pin down what exactly got leaked. So how do we reduce the risk of cloud computing? Well, of course, encryption should be our first line of defense, making sure that data that's in transit as well as in storage is encoded so that it can only be read by the data owner. We also must carefully choose the method by which our network connects to cloud resources. So is it going to be connected directly through the internet? Are we using remote access connections like VPN? Are we using a leased line or dedicated connection? These are all critical aspects of how we deal with reducing our risk. Now, encryption, the use of mathematical code, traditionally called a cipher, to scramble data into the format that can only be read by reversing the cipher, is generally used to keep information private and primarily evaluated by three benchmarks: confidentiality, integrity, and availability. These three terms form what's called the CIA triad of the standard security model. So if you work in InfoSec or if you work in IPSec, you do hear quite a bit about the CIA triad, making sure that data is only available to the people that it belongs to. The data that's provided or displayed is the original data given, and the availability of that data follows the model of we say it's going to be available at this time, it is available at that time. So with that said, let's talk about key encryption. Now, a key is just a random string of characters that is woven into the original data and generates a unique data block called ciphertext. This is usually created according to a specific set of rules, which we refer to as an algorithm. Key encryption can be split into two categories, public and private. Private key encryption means that the data is only dealing with a single key. This is known as symmetric encryption, so the same key has to be used during both encryption and decryption. This is a key known only by the sender and the receiver, so two people with the same key. Public key encryption is asymmetric, so the data is encrypted using two keys. The private key is known by the user, and the public key is known by anyone who can request it. So a public key server is a freely accessible host and provides users public keys. So this means that an individual can create a block using a public key, but it can only be decrypted by the private key. So the key pair is a combination of public and private keys. As I said, because it uses two keys, it's asymmetric. And in order to find information about the user's public key as well as some identification information, we use what's called a digital certificate. The digital certificate is issued and maintained by what's called a certificate authority, which is a trusted company that will find different ways to verify a particular user, to verify or vouch for them that they are who they say they are. So they provide a figure of integrity by which we can rely upon a particular digital certificate. PKI, or public key infrastructure, is the use of certificate authorities to associate public keys with certain users. IPSec, or Internet Protocol Security, is a protocol suite that defines rules for encryption, authentication, and key management for TCP/IP transmissions. There are 5 steps to the secure connections for IPSec: initiation, key management, negotiation, data transfer, and termination. So we notice that the first and last are initiation and termination, meaning that we have to open and close the connection deliberately. There are 2 different modes in which IPSec operates: transport mode and tunnel mode. Now both are methods of encrypting TCP/IP transmissions, including the web pages and data entered into web forms. Both protocols work side by side and are known widely as SSL/TLS or TLS/SSL. When a client and server establish a connection of this type, they establish a unique session. There's an association created between the client and server defined by agreement and a specific set of encryption techniques. The SSL, or Secure Socket Layer Handshake Protocol, establishes this session. Transport layer security is also included. The handshake protocol allows the client and server to authenticate similarly to a TCP three-way handshake. There's a variation called DTLS, Datagram Transport Layer Security, that is designed specifically for streaming. Because remember, TCP and UDP use very different methods of associating a connection between 2 devices. Applications using DTLS must provide their own means of packet reordering, flow control, and reliability assurance because, as we know, UDP does not provide any of those functions. DTLS includes security levels that are compatible with TLS and is commonly used by delay-sensitive applications such as VoIP and tunneling apps. With that said, very common application for SSL and TLS to ensure we have a strong connection is what's called remote access. Remote access allows us to log in to a server in a different geographical location and act as if we were physically present. We can authenticate subscribers to a particular service and treat them as if they were local. This requires a type of what is called remote access server, or RAS. The 2 types of remote access servers we traditionally deal with are dedicated devices or are software-based, so hardware and software-based remote access. We can also have a point-to-point connection over a dedicated line, terminal emulation, called remote virtual computing, or a VPN. Now, data is often encrypted before it's transmitted over the connection. Some remote access protocols will natively include this. Others must be paired with a specific protocol. So in the early days of remote management for switches, for instance, A lot of what we talk about is SSH versus Telnet. Telnet does not include any specific encryption, but SSH does. So in certain cases, if you want to use a very specific encryption protocol, you could use Telnet, provided that you made sure it was paired correctly with that particular encryption protocol. There's an older protocol known as SLIP that we used to use, which has now been replaced by PPP, or Triple P, as the preferred communications protocol for remote access point-to-point. So PPP is a data link layer protocol that directly connects two endpoints of a WAN. The PPP protocol, or PTP protocol, can negotiate and establish a connection between two computers, use an authentication protocol to make sure that a client and a remote system are able to verify one another, support several types of network layer protocols, and encrypt transmissions. Although PPP is considered fairly weak by today's standards, we do also want to augment that where we can. Terminal emulation through remote virtual computing allows us to assume control of a computer across a network connection. So bringing it back, Telnet and SSH. Some different GUI-based software that we use that's similar to this is going to be Remote Desktop for Windows, Join.me, VNC, and TeamViewer. I prefer the command line based stuff simply because it tends to be a bit more robust in terms of being able to script things. Telnet allows us to connect to a device remotely, but provides little security and no encryption. SSH is a collection of protocols that provide for both secure authentication and encryption and guard against a number of security threats. So let's say that we have something that's trying to perform unauthorized access. SSH can take care of that. We can also have a prevention of IP or DNS spoofing, as well as protection of data in transit. So when we talk about information security, we often have to remember we want to protect data not only that's being stored locally, but as it's in transit between devices. SSH is developed by SSH Communication Security. Depending on your version, it will require a license fee. There are some open versions of this, like OpenSSH. A secure connection requires that SSH be running on both the client and the server. So when you go into Net 125 and you do configure a Cisco switch, a lot of times you'll use the command transport SSH input, or transport input SSH, excuse me, to make sure that SSH is the functional model, so that way you can secure connections for remote connectivity. This allows for password authentication using both public and private key generation. Configuration options use one of several encryption types, requiring a client password or performing port forwarding. Port forwarding is where we redirect traffic that would normally use an insecure port to a port that has been secured by SSH. So here we see the PuTTY interface. This is very similar to something that we would see in Bash or TerraTerm, depending on what interface we're using. But you can see here several of the settings that we would need to point in. So we can point in the IP address or host name of the device we're connecting to, on what port we wish to connect, and then if we want to save our session, quote unquote, that allows us to save things like our username and software interface, things like that. You look down below on the left, you can see the connection types, SSH, serial, or proxy-based connections. You can save your settings in there. I don't tend to recommend that simply because that makes it easier for somebody to log in, but if you do have a fairly complex login and all you're doing is reserving your password, you can save your username and all of your configuration steps. RDP, Remote Desktop Protocol, and VNC, Virtual Network Computing, are system protocols that are traditionally used with Windows. So RDP is Microsoft proprietary. VNC uses the cross-platform protocol Remote Frame Buffer, or RFB, to remotely control a workstation or server. VNC is open source, so a lot of companies have developed their own software that can run OSs on client computers and remotely control not only desktops, but laptops, tablets, and smartphones, as well as media equipment and surveillance systems. Now, management URL using HTTPS is where we have a networking device being configured through a computer browser. This navigates directly to a management URL. The user can then make changes directly to the device through that interface browser. Ideally, the devices will require an encrypted connection over HTTPS. If they don't use HTTPS, I would be very curious as to why. Out-of-band management, this is a term that we talk about dealing with out-of-band versus in-band services for a device, meaning that we have to set up network-based services first, we have to set up encryption and all of the different terminal management functions. So a remote management card is attached to the console port, or sometimes is built into a device. And then sometimes we'll have that particular device provide link management for all linked devices. So if we have a server, a console server, if you will, and it uses out-of-band connectivity to a different device, you may be able to manage multiple devices through their switch ports. Remote file access, traditionally we'll use what's called FTP, File Transfer Protocol. It's not a form of terminal emulation, but does provide remote file access. This is how you download stuff from a website, by the way. Related to FTP would be FTPS, which is FTP Secure. Secure FTP is a little bit different, but they're pretty close in terms of functionality. And then TFTP, which is used for very small files, usually for configuration and things like that. VPN is where we create a remote connection privately from end to end from a local host to a connection on site for a different area. So graphic 724 gives us a good indication of what this does. We have a central office in Seattle. We have 3 branch offices, one in Los Angeles, one in Detroit, one in Charleston. Through the VPN gateways for each office, we are able to have direct connections over the internet using tunneling to be able to connect between sites as if they were physically contiguous. VPNs can classify themselves using 3 separate models: site-to-site, client-to-site, also called host-to-site, and host-to-host. So here we have a couple of things in our neck of the woods. We've got a branch office in Charleston with a VPN gateway connecting to a mobile client in New York, a remote office in Raleigh, and a telecommuter in Asheville. So, we've got some Carolina representation in here, south and north. These are showing site or client-to-site representations from New York to the VPN gateway in Charleston. And then we have site-to-site between the remote office in Raleigh and the VPN gateway. And then we have a little bit of host-to-host if we had a direct connection between the remote office in Raleigh and a telecommuter that was remoting into said office. So if we were to assume that one of these desktops on the far right were actually a VPN connection, you can have a tunnel to a tunnel. You can join tunnels together. A router-based VPN is the most common implementation on Unix-style networks, and server-based VPNs are most commonly on Windows. There are also devices that we call VPN concentrators. These are going to authenticate our clients and establish tunnels as well as managing encryption. VPNs tend to use 2 primary encryption techniques, SSL and IPsec. An enterprise-wide VPN can include elements of both client-to-site and site-to-site models. We can see here the difference between a dotted line connection and a solid line connection, referring to site-to-site and client-to-site. DMVPN, Dynamic Multipoint, is a type of enterprise using Cisco devices. It dynamically creates our VPN tunnels between branch locations as needed, instead of needing to have constant static tunnels for site-to-site connections. So that way, if we have a lot of information that's transferring between 2 remote offices, we can create a dynamic, secure VPN tunnel, pass information back and forth, and then be able to close that tunnel as needed. To ensure VPNs can carry all types of data securely, there are special VPN protocols that encapsulate higher layer protocols known as tunneling. So many VPN tunneling protocols operate at layer 2 and encapsulate the VPN frame into a standard network layer packet. Some VPN tunnels will actually work at layer 3. This gives us some additional features, but the important part is the payload that is then opened up is not the same thing as the payload would be if it were a standard non-VPN frame. Most tunneling protocols rely on an additional encryption protocol to provide data security. So we may use something like PPTP. So this is not the same thing as PPP. This is PPTP. This is an older layer 2 protocol that supports all of the necessary VPN protocols and services in that suite. It uses TCP segments at the transport layer and is no longer considered secure. So it can be used, but it's not considered secure. And something I will tell you, a broken form of encryption is actually worse than a non-broken form that's kind of weak, because we want to, very much like in programming, if something breaks, I want to know. I don't want it to operate just kind of as is. If something fails, I want it to fail to the point where I know what's going on, so that way it's not just passing data back and forth, leaving the door open, as it were. L2TP, Layer 2 Tunneling Protocol, encapsulates PPP data in a similar manner to PPTP, but it's implemented with IPsec for extra security. You can connect a VPN that uses a mix of types, so you can go router to router, router to RAS, or client to RAS. Generic routing encapsulation can also be used in conjunction with IPsec to transmit PPP, IP, and any other kind of message through the tunnel. So L2TP and GRE are a little bit more common. OpenVPN is an open source VPN protocol that uses a custom security suite called OpenSSL for encryption. OpenVPN is very common with a lot of VPN systems. If you use something like Nord, or if you use IPVanish or VPN Unlimited, you can actually get your certificate keys and your general certification config from that program and use OpenVPN instead. I like OpenVPN a lot of customization. IKEv2 is a component of the IPsec protocol suite. Fast throughput, a lot of stability moving between wireless hotspots. So if you're using VPN and you are mobile, there's going to be a lot of IKEv2 traffic for you. Now for remote access, we have some requirements we have to deal with. Devices for remote access must be kept patched, updated, and firewalled. Device access must be controlled by a strong password or biometric measures. I would also insert or both. Passwords need to be strong and changed periodically. If you're unsure about password strength, there's a number of different documents out there. Some of the biggest things are length and complexity, making sure that you're incorporating upper and lower case, numbers, special characters where possible. Don't use dictionary words. Don't use personally identifiable information such as birthdays or your child's name or favorite sports team or your pet's name or things like that. There's a lot of social engineering stuff out there these days, especially with social media, that can break those passwords much more easily. A device's internal and external storage devices must also be encrypted. So if you're going to work on remote access, you need to make sure not only is the data being encrypted, but the data that's local, the device itself, has to be encrypted. Any customer and company data that is accessed, transferred, stored, or printed must be kept secure. Any loss or theft of devices used for remote access must be reported immediately. Encrypted VPNs must be used to remotely access company resources, and while remotely connected, the device must not be connected to any network not fully owned or controlled by the employee. I've had some first-year students not know this. You can actually be connected to multiple networks simultaneously, and if that is the case, you want to make sure that with a VPN, you disengage from any of those networks, because you're not trying to facilitate transfer of traffic to anything that is not secured as part of the same VPN process. Now, VMs are a little bit different because depending on their configuration, as you saw earlier, their NICs may not necessarily contact one another depending on how they're partitioned. Again, the data requirement is more so going to fall in your organization's declaration of acceptable use and will depend on what their particular standards are. If you're responsible for those standards, then you might want to do a little bit of road testing, a little bit of research before you finalize it. Remote sessions must be terminated when not in use. So remember with IPsec, we had to have initiation as well as termination. VPN should have no difference. Anytime you create a VPN session, it needs to be able to initiate and terminate safely. So when in doubt, err on the side of caution. Have it time out after 60 seconds of inactivity or something similar. That's chapter 7. So if you have any questions or concerns, of course, we'll go over just the basic contact methods as we're stepping through the summary here. Hopefully today was enlightening. If you have any questions, you can always email me at jearmke063@cfcc.edu, or you can contact me via my Google Voice number 239-7814, or just swing by the office and say, hey, I'm always glad to have clients come by and visit, of course, with 6 feet of separation and a face mask. Hopefully you guys are all staying well. If you have any further concerns beyond that, I'm always glad to hear them. So swing by, say hey, and we'll have a chit chat about whatever's going on with you. I wish you all the best, and I'll catch you next class.